Thank you, Philip. Yes, we have Frank Pollmann from the TU Munich talking about efficient simulation of quantum transport in 1D. Let's give him a warm welcome.
Good. Yeah, thanks for this nice welcome, and thanks for having me. So let me just minimize this window a little bit, put it aside. So I can see some of you. Good. So now I think it works. So yeah, as mentioned, I want to talk about efficient simulations of quantum transport, and what I want to show in particular is that certain far out of equilibrium properties of quantum many-body systems can actually be evaluated efficiently on classical computers. And the key idea that makes this possible is that we can help an algorithm to efficiently forget information that is not required for our purposes. So this is basically the point I want to make. And let me also stress, and this is, I think, particularly important for online talks, please interrupt me whenever something is not clear. I'm happy to pause or to just provide additional information. So
yeah, we have no problem doing that.
Good. My nightmare is to talk into the void for a long time.
Yeah, I know that's very difficult. Yeah, we will keep it interactive.
Good. Okay, so the work that I'm presenting has been done with these two gentlemen, with Tibor Rakowski, who was a student in my group and moved to Stanford for a postdoc, and Kurt from Kaiserling from the University of Birmingham. So before diving into explaining the ideas of the algorithm, let me just roughly set the stage and the questions that we are interested in. So the setting is now that we prepare a system into a state which is far out of equilibrium. So for example, we could say that, well, we just have a system with particles, and these particles might be just placed somewhere into our box. And now we take this state, which is not an eigenstate of the Hamiltonian of consideration, and evolve the state. As we evolve the state, it will follow in the beginning some extremely complicated microscopic dynamics, which we would find very hard to capture. In the long run, if we just let the system evolve for as long as it takes, it is expected generically that the system will approach an equilibrium state, which is then described by a few conservation laws. So for example, if we have a Hamiltonian, which means that the energy is conserved, so we have a temperature which is describing the final state. If we have a conserved particle number, there will be a of chemical potential describing the final state. So if we wait very long, the system will just approach an equilibrium state. And now, basically, in between, there's an interesting regime where the system is expected to describe by hydrodynamics. In particular, if we just now start, for example, with a particle distribution which is very inhomogeneous, we expect that there's some sort of a local thermalization time, and then the system is described by some inhomogeneities in the density, and then the system will follow some potentially simple equations to approach then the final equilibrium state. For example, if we have a system with particle number conservation, the system will follow a fixed law leading diffusion, or yielding diffusion. So for example, and this is now shown in this right plot here, we could say that we prepare an initial state where it has the very large particle density at the very center of our system. And then as we go along, the particles will diffuse over the system, and we could just describe it by this diffusion constant. So in particular, this initial delta peak that we might have started from for the particle density will develop a Gaussian with a width that is increasing as the diffusion constant times the square root of t. So basically just having certain conservation laws allows us to predict this diffusive behavior, and it is then described by a diffusion constant d. So now a very specific question we might ask is, given a Hamiltonian H that we are dealing with, what is the diffusion constant d? And this is exactly the type of question we want to ask, namely, given a specific Hamiltonian, how can we numerically extract this diffusion constant d for a given microscopic model? And that is, in principle, a quite difficult question, because if we want to simulate it exactly, we just have to prepare our microscopic state and we have to evolve it. And that would be something that, generically speaking, is exponentially hard. And let me now first discuss some very brute force methods.
Can I ask a quick question?
Sure.
So I guess here you're basically thinking about particle systems. Is there like an analogous hydrodynamic relaxation for spin systems?
Yes, definitely. Thanks for asking. So if you have now a spin system, you could, for example, have a system where the total SC is conserved, right? If the total magnetization is conserved, then you can just simply replace
then you basically have
number.
Particles in you can regard ups and downs as particles or no particles. So I guess it's very similar. Like when you don't have
right, and now if you say that you have a system where you just maybe take an Ising model where you do not have particle number conservation, you still have energy conservation, and then you can just prepare an initial state where you have like a lot of energy pumped into the middle, while elsewhere it might be in the ground state. And then you will also expect a diffusive behavior of the energy density.
I see. Thank you.
Mm-hmm.
So you always at least have energy.
Say it again?
Sorry, you always have at least energy as a conserved quantity, you're saying.
In Hamiltonian systems, yes. But you can also just move away from a Hamiltonian. You could say that you might have a Floquet system, where you just switch between systems, or you can have a random unitary evolution. So even you don't require energy. You only require a conservation law. And in fact, you can show this kind of behavior also for random unitaries, that you just add a particle number or a spin conservation. So this is fairly general. I just give Hamiltonian here as an example, but it goes beyond it.
I see. Thank you so much.
Yeah, thanks for asking.
May I ask a question as well?
Yeah, sure.
So I was just wondering, how do you characterize equilibrium, as in the non-local equilibrium? Because this is time evolution under a Hamiltonian with unitary time evolution operator, right? And the initial state not an eigenstate. So how do you characterize the non-local equilibrium?
So just to rephrase, just to make sure that I understand what you're asking. So basically you're asking how do I tell that eventually I converge to an equilibrium state?
Yes.
Right. So this is also an excellent question, because of course the system is not an eigenstate. It will never be an eigenstate. So I can always find something that will keep changing as I go along in time. But what I want to do instead is, I would, for example, take my system and I let me just even do it, and I would just draw a box. Let's say I take my system, I draw a box of a certain size. And now what I'm going to do is I would look at the reduced density matrix for my small subsystem, right? So I have now a reduced density matrix, rho r, just describing the degrees of freedom inside of my box. And what I demand is that the reduced density matrix of the system, describing whatever local measurement done in this box, will basically not change as function of time. And then the conjecture is, for systems that do this equilibration, that I can actually replace the reduced density matrix by a thermal density matrix, which for systems with energy conservation, for example, will be described by a temperature or inverse temperature beta.
Yeah, thanks. So I was just wondering, how is this different from local equilibrium? I mean, is there something limit to the size of the system, the box which you're looking at?
Well, strictly speaking, I do want to have something which would, I require a box which is somewhat small compared to the total system. And this you can see for the following reason, like assume that you would just have a box which includes almost the entire system. In that case, the entropy of the reduced density matrix is limited by the remainder of a system. So it can't really be a thermal density matrix having a full volume law, or having then basically the entropy of the density matrix can't be extensive, which you require for a thermal state.
Right. So I was just thinking that isn't this local equilibrium, and like, how do you distinguish local equilibrium from this notion of equilibrium? I mean, is it something to do with as the reduced density matrices for which you can describe using a thermal density matrix, the size grows, and once you read a final size, is that when you have non-local equilibrium, whereas local is defined for maybe one site or two
No, but
sites?
I mean, I wasn't making a big point of right. So right now I see your point. Sorry. So by my local equilibrium, I'm saying that here, for example, if I just draw a box, in a small box, I do reach a thermalized state. So basically, if I just draw a very small box in this picture here, I would see that, well, here I'm having a density matrix or reduced density matrix describing the small box here, and I'm having a density matrix describing it here. So locally, it is equilibrated. But if I just basically wait long enough, I see that the particle number is still changing. It looks as if it's a system, it's like a thermal system, like it's just having a slow time scale on which it is still changing. While here we really reached a thermal state. I think this is the definition by having here a local thermalization, but here it actually just is a completely homogeneous state.
I see. So I guess I was thinking of local equilibrium as what you called equilibrium, and that's probably why we were not understanding each other. Thank you.
Good, thanks. Good. So just to briefly recap, so now we have a given Hamiltonian. We just prepare an initial state, and from what this we want to extract this diffusion constant. Now the question, how do we do this? And the first way of going at this problem is probably what we would do is we just exactly simulate the time evolution of this many-body system. So we would just say that, well, let us prepare the initial state. Let us now evolve it with the Hamiltonian. The problem is that the preparing the state exactly is extremely hard. In particular, the Hilbert space dimension is growing exponentially with the system size, and then we have to store and manipulate these exponential number of amplitudes in the many-body wave function, right? So we find that the complexity or the difficulty of this problem is scaling exponentially with the system size, and if we just look what we can realistically do, we will find that the total number of spins we consider is of the order of 30 or so. And that is often not sufficient, because often the time scale or like the length scale on which it take which are required for a system to locally equilibrate, to just go into this hydrodynamic regime, might easily exceed these 30 or so spins. So this method is quite limited because of the size constraints. So, but then we might say that, well, there are other powerful tools, and for example, so-called matrix product states. And I'm not going to give a full detailed introduction to what matrix product states are, but I just want to flash basically the key idea. The key idea in matrix product states is that we say that, well, previously the big problem we have is to store the amplitudes of the many-body wave function, because here we have an exponential number of parameters, right? So it's a mathematically speaking, it's a tensor of order L, and this order L tensor has an exponential number of parameters in it. And here D is now the local Hilbert space dimension, which for a qubit system would just be 2, and we get then D to the L complex numbers. And now the key idea of matrix product states is that we say that, well, let us now parameterize, or like let us now just approximate the amplitudes in the many-body wave function in this form. So basically, for every physical degree of freedom, which for a qubit system can be up or down, we just write down a matrix of a given dimension. In the simplest case, if chi is equals to 1, this would be just amount to a product state where the amplitudes of the total system are just the product of the amplitudes of a local state. And now we can just, with this ansatz, basically interpolate, if you wish, between a simple product state and a fully highly entangled state by just increasing this number chi. And for a general state, if you just take the most generic state for a given system, this value of chi will actually increase exponentially with the system size. But the hope is, and there's some good reason, even you can prove it, that if the state that you are looking at has only little entanglement, little many-body entanglement, then you just get away with a fairly small one-dimension chi. The upshot is, and this is what's really important, is that if this is justified, we actually can manage to reduce the number of parameters from something that grows exponentially with the system size to something that grows only linearly with system size. And that's actually extremely helpful for many simulations, etc. So one technical thing that we're going to come back later on is we can just use a sort of graphical notation for working or for dealing with these matrix product states. In particular, I'm just shown here on the right-hand side. We can now draw pictures where we say that the tensors in the matrix product state are just a blob, and for every index there's a leg sticking out, right? So we have now the physical index, which is J, which is just say 0 or 1 for a qubit system, and we have the virtual degrees of freedom alpha and beta. This is now the index which we just contract over when multiplying all these matrices. And then the matrix product state can then be represented by this this structure here, where we just now contract over all these virtual indices and just leave out the physical indices. And this is now becoming the amplitude in the many-body wave function. So states that have little entanglement can be represented efficiently. And this kind of brings us now to figuring out the scaling, because it means if we now prepare a very simple product state where the particles are, or the spins are just localized somewhere in space, that state is easy to represent because it has no entanglement. It's a product state. But as we time evolve the state, we are running then into a problem, because then the entanglement is growing, or is expected to grow linearly as function of time. And thus the complexity or difficulty of representing the state in terms of a matrix product state is expected to grow exponentially in time. So taking these two approaches now together, we're just ending up with the plot here shown on this slide, on the side. Namely, if we just using exact diagonalization, well, we are not limited by time, but we are limited by the system size. If we are just using this matrix product states, well, we are not limited by the system size. We can just represent basically systems as large as we like, but we are limited in terms of the time that we can simulate it before running into memory issues on the computer. So this is now basically setting the stage. This is where we want to find a way to just get into this wide area here somehow. And And the reason why I'm at least somewhat hopeful that this is possible is now summarized in this plot, or might call it this information paradox. And keep in mind, we at this moment, what we are interested in is the observation of some local quantity. So we want to just measure something inside our box that I drew. So and then we have now the following picture in mind. So we're starting now from a state that's very simple to represent. So we just need only very few qubits, or we need very few bits on our computer to store this state. If we now do the time evolution using matrix product states, well, the number of parameters is growing exponentially, so it's getting much harder to simulate. But this is sort of in contradiction with what I stated before, because if we go to very long times, the local quantities are again very easily described. I can just describe it by my local density or my local energy or like a temperature. So that's again becoming easy. So the question is, and this is now the core questions I want to address, is how can we actually truncate entanglement without sacrificing crucial information on physical or local observables? So this is now the question I want to address in the following. And this question, I mean, I'm not the first to ask this question, and I'm just giving a selection of a few papers here where exactly this question is addressed using different means. And let me first, before coming to the main part where I want to introduce this algorithm that we are quite hopeful about, let me just show some idea that I was very excited about, but it turned out to fail. So the first idea that we were entertaining is the following. As I pointed out, matrix product states are a good way to describe the state at the very beginning. And then the idea was, well, let us now follow the following procedure to evolve the state. So basically, what we would like to do is to simulate the Hamiltonian dynamics using the time-dependent variational principle. In particular, we are saying that, well, we want to understand the dynamics of our Hamiltonian age, and let us now project the Schrödinger equation into the manifold that is described by this matrix product state. And what we then get is roughly the following picture. So we start from our product state. The product state can clearly be perfectly represented. And now we just do the time evolution. In the short time evolution, that's great because we are staying in this space or in the manifold of states that can be represented in terms of our small bond dimension MPS. So up to here, we are not doing anything fishy. We're just simulating the dynamics exactly. Now we just move on in time, and well, it still works. But at some point we hit the boundary. At some point, the exact trajectory would take us out of the manifold for our matrix product states. But at this point, if we are just following the TDVP equations, well, it doesn't leave it because it doesn't leave the manifold because we are projecting it back. So we now follow a trajectory which is maybe at the boundary of this manifold. This is kind of a graphical illustration of how I imagine that this looks like. If I'm following this trajectory, the Hamiltonian or like the effective classical Lagrangian that I'm effectively simulating has actually the same global conservation laws, such as energy, particles, etc. So a hopeful but not really justified expectation could be that you say that, well, it's a now classical system which has the same global conservation laws as your quantum mechanical system has. So it might also have the same universal properties, in particular that the diffusion constant you get for this classical system would reflect exactly those of the quantum mechanical system because it has the same conservation laws, right? So this was a hope that we had, but it turned out that these hopes were not. The universe was not as nice as it could be.
May I interrupt and ask you another question?
Sure.
Yeah, thanks. So I was just wondering, the energy conservation is a property of, getting technical here, one-side TDVP, right? And it's not preserved perfectly in two-side TDVP. And is
That's
it
exactly correct? Yes.
Is it reasonable to assume that what you're going to show uses two-side TDVP?
No, what I'm showing is like exactly. So,
no,
like
what you're about to show. As in, like,
for one-side.
Okay.
No, that's a good point you make, because if I'm using two-side DMRG, right? So sorry, like, because there's now the following story. So if I'm using one-side TBD, I'm exactly moving in this manifold. So I'm following the trajectory. If I'm using two-side DMRG, two-side TDVP, actually I'm allowed outside of this manifold. And then I'm doing the truncation back, and this step, when I'm projecting it back, would no longer obey the conservation laws of the original Hamiltonian. So then the whole story would not work at all. Like, this reasoning that I'm doing here wouldn't work at all.
Yeah, thank you. That was my question.
Because if I do this projection stack, then for example, energy wouldn't even be conserved. Meaning, if I would look at the diffusion, or like if I basically just create my energy package, and then energy is not conserved anymore, it would just the correlations, the energy correlations would decay exponentially, and I would just really get a qualitatively completely different behavior.
Thank you.
And exactly, now we have an algorithm that does conserve all the symmetries, and we do get diffusion, and this is now summarized basically in this plot here. So if we just take, for example, an XXZ model with longer range interaction, so we have this exponentially decaying interaction in this model. So this is in a way a generic non-integrable model, and we can now just play exactly this game. So we just create a wave package and let us spread over the system. And now what we see is that both at short times we just see a diffusive behavior. So the sigma squared grows linearly as function of time. So we get a diffusive behavior at short times. And also we get a diffusive behavior at long time. So we do find diffusion as expected. However, the diffusion constant D changes the moment that we start to not follow the exact trajectory. And in fact, if I'm just using other methods, the black line is about the correct one, and the red one is now the one of this effective model of this effective Lagrangian. And while it does not work for this model, there are some other regimes or some other models where it just happens to work, but that is more or less accidental. But the generic case seems to be that this approach fails. That meant that we just basically went back to the drawing board and tried to come up with a different idea, right? So now basically letting the system just evolve and ignoring the fact that it's not doing the right job didn't work. So now we just were thinking.
May I interrupt again and ask you again?
Sure.
Sorry. Can you go back to the previous slide?
Sure.
Yeah, so one thing you said was there's a notion of time scale at which this you see the hydrodynamics at which you get the diffusion properties. So I was just wondering, in this plot, what is that time scale? And if it is less than, say, 7.5, then maybe I'm getting the diffusion coefficient right with Pollmann dimension 8.
Right. No, thanks. That's a very good question. And in fact, I was just going through quite a few number of different models to get a plot like this, because indeed, as you say, very often you might say that so indeed you just might have a scenario where you just get something, whatever non-universal behavior, and you might say that, well, what we find here indeed is actually the long time limit. And here, this model and also the parameters chosen for this model are actually in such a way that we are quite confident that the model is actually is very mixing. It's basically designed in such a way that it reaches this local equilibrium very quickly. And I just also did some large scale exact diagonalization data, and this one keeps to go on forever, as far as I can tell. So I think it's highly unlikely that this is actually the correct behavior at long times.
Now, I was wondering is that if you want to get D equals 3, you can get that, say, before T equals 7, right? And if that's what you're looking for, then haven't you gotten that already?
Right, but for this model, yes. I mean, this
oh, okay, I see. Okay. So it's an accident of this particular model.
If we just use other models, and you just might indeed get something that has whatever kind of non-universal behavior, and only after very long times shows this. But then I mean, I wouldn't get to this regime with this ansatz at all.
Okay, yeah. Thanks.
All right. Good. So basically, then we were a bit unhappy with this method, so it didn't work. So we just were trying to come up with something else. And just to aid this intuition that we, or to try to give you some idea about the way that we are thinking, is that if we are just following these TDVP equations, the system doesn't really know much about the physical properties of a system. So what I mean by this is the following. So if I'm just projecting to this manifold of matrix product states, the only thing it cares about roughly is to have a state which is close to the other state with respect to some L2 norm. So this is roughly what's doing it. It doesn't really know, it doesn't really have a very good physical intuition about the observables that we want to calculate eventually. And basically, it's just sort of truncating the entanglement based on getting something that is close to the state using, I think, something like the L2 norm or some sort of global minimization of the L2 norm, norm difference. So then we just thought about how can we just truncate entanglement using some physical intuition, and then this is what we then did, and the idea is now just in a few words the following. So we just change from the Schrödinger picture that we have been discussing so far to the Heisenberg picture. And in the Heisenberg picture, we are just introducing some artificial dissipation, which leads to a decay of operator entanglement. And then in this picture, we can then represent the time evolution of the operators up to very long times. So that's the key idea, that we are now introducing an artificial but sort of well-motivated dissipation on the operator evolution. Right? So we are not doing a physical system in the Schrödinger picture where we just couple it to a bath, but we are just now having these super operators, evolving operator like super operators that have some dissipation, and the way that we want to dissipate or add dissipation is that we discard information corresponding to complicated endpoint functions, which we believe eventually won't play a big role. And the error that we then have is due to backflow, and here we can actually argue that this will be exponentially suppressed in terms of our parameter L star that I will introduce in a moment. Right? So we just introduce an artificial dissipation in the Heisenberg evolution of operators. And what we are going to do is we are just discarding information related to complicated endpoint functions. Let me now give you some idea about how we do this in practice. So in order to calculate or to estimate diffusion constants, etc., what we will do is we will calculate correlation functions at infinite temperature. Right? So we're just now assuming that we have very high temperatures, and we want to calculate now expectation values of this type. So we just take some operator Q acting at site 0 at time 0 and correlations with some other operator at site X at time t. Right? And from this, or even like from the autocorrelation function itself, we can then estimate the diffusion constants. And this we calculate now in the Heisenberg picture. And in the Heisenberg picture, or like in general, like if we just are in an operator space, every operator that we have can now be expanded in terms of polystrings. I mean, now we are assuming that we're just having qubit systems where we have just a two-dimensional local Hilbert space. Right, so now we have the space like polystrings consisting of these 4 operators, like the identity, poly X, Y, and Z. And now we are introducing the artificial dissipator. And let me just take a moment to explain what this dissipator is doing. So if we just apply this operator, or super operator, D, L star, and gamma to a polystring, it's doing the following. If LS, and LS is now defined in the following way, LS is now counting the number of non-trivial poly operators. So here we have just a product of identities, and we have just a single sigma x here. And here LS is equals to 1. The second example here is we have a poly Y, then we have identity, then we have poly X. Here LS is equals to 2 because we have 2 non-trivial polys. It doesn't refer to the distance between those. It just corresponds to how many non-trivial polys we have in a given string. And the last example here is LS equals to 3 because we get 3 non-trivial polys. So now if we just apply the dissipator to a polystring, it just gives the string back if this quantity LS is smaller than the given L star. If the LS is larger L star, it will have this exponential damping. So it will just reduce the weight of this state of this polystring in the operator. Right. So we have now a cutoff length, which corresponds to the number of accepted non-trivial polys. And is there a question? Okay, so okay. So now this L star now has to be chosen larger than the support of the conserved quantity we are interested in, right? Because if, for example, we are interested in energy conservation of a 2-side Hamiltonian, then L star has to be larger or equals to 2, and so on, right? So because otherwise the conservation laws will be destroyed by this operator. But as long as this is the case, we are good, and we just still conserve the these symmetries. And now, if we just introduce this operator, oh, there's a question. Okay.
No, actually, I do have a question. I was puzzling through it, but so I just want to make sure I'm following. So in the Heisenberg picture, this is still for the closed system, but we are introducing dissipation as a way to model scrambling. Okay.
Yes, that's exactly correct.
Okay. It's just I'm like, well, this is closed. Why do we need super operator? Okay, but I think I'm following. Okay, thank you.
Exactly, it's like an artificial dissipation that we're just using here as a tool, right? Right, and now now coming to the modified evolution that we are doing now, and this maybe also aids the intuition, I guess, because now, as I pointed out, we want to calculate now the infinite temperature correlation functions for our operators, and that amounts to just taking the trace of this product. So basically, it's now the overlap of those two operators, which means maybe in simplest case, think about calculating just autocorrelation functions. Then we just start from so we would start then from a very simple operator, which would be just identity, sigma x, identity. This would be our starting point for the first operator. And then at the end, we're just measuring again, maybe 1, 1, 1, sigma z. So we're just calculating the overlap between these. But what we then see that the only terms or the only paths that contribute to these correlation functions are those that return to a very simple polystring in the end. And the intuition is now that if a certain path wanders off to horribly complicated operator, then it will just very likely to not return to become a simple operator that would actually contribute to our measurement. And this is now what's going to happen, because if there's a path that just goes directly, it's not at all affected at all by our approximation. If they just wander off, they are now just increasingly damped because of this gamma, right? So the larger gamma is, the more or the stronger that the damping is of those contributions wandering off to the dark side here. Right, so that's just basically the intuition behind the whole idea. And the key assumption, I just said it in Word, but here's also now written. So the key assumption is that the backflow from long to short operators is weak, and that's also related to what's this kind of short memory time in the Moritz-Zwanzig memory matrix formalism, but here now turned into a practical algorithm, if you wish. And why do we want this? So the reason why we actually are happy about doing something like this is that the operator entanglement, which in turn is directly related to the representability of a given operator, is reduced. Because now if we just cut off all these complicated terms, we just make it easier to represent the operators using the matrix product state or the matrix product operator formalism. So just to put this all into perspective, very early on, I just made the point, matrix product states are a good representation when the entanglement is low. Now we just shifted to the evolution in terms of operator space, but we can turn these operators formally into states and just represent them using the same framework. The problem is, if I'm just in the Heisenberg picture, the entanglement of those operators is still growing. But then that gives us now a very controlled handle how we can reduce the entanglement and then still represent them efficiently using matrix product states. And here, I mean, in interest of time, maybe I just not going into detail, but there's actually an analytic argument for why this backflow is actually exponentially small in our L star, and we can do some numerics and backing it up. So we just see that the error we make on this due to this backflow is actually decreasing exponentially as L star. So we can use this as a control parameter to make sure that our algorithm actually converges. But I'm going to show some numerical data in a moment backing this up. So now let us now assemble this to a working algorithm. So, and this is now shown here schematically. So we start now from our initial state, which tends to be a very simple operator, just maybe a product of identities and just a single non-trivial poly in the middle. And now we just use some standard technique for doing time evolution of matrix product states, for example, the time evolving block decimation algorithm. And now we do it for some time, let the entanglement grow. And then we just apply this superoperator. And the superoperator can actually be represented itself very efficiently using a low-dimensional matrix product operator. That's a technical detail, but it's not hard to apply it in this formalism. So what we then have is now that we just do the exact time evolution, now kill off or reduce or damp complicated operator, do exact time evolution, and so on. And this is now the algorithm which we conjecture to be a reasonable one, assuming that backflow is not so relevant for the for our observables. And now we actually can do the following. We can now plot the von Neumann entropy, or the entanglement entropy of our operators as function of time. And we see indeed the behavior that we were hoping for. We see that on short time scales, the operator entanglement is actually increasing. So the bond dimension required is increasing. But then if we just do this artificial dissipation, it indeed pushes down the required entanglement entropy, and we can now simulate it exactly, right? So which means that formally bond dimension was our problem because it was just building up more and more entanglement, so we couldn't really represent the state. Now with this artificial dissipation, the entanglement entropy is actually no longer growing as badly, so we can actually simulate it without additional truncations. So which means that the only approximation that we are doing is the one that we are just getting from our artificial dissipation, but no longer from the truncation due to the matrix product state representation. And for this artificial dissipation, at least we have a hand-wavy argument why this shouldn't bother us too much. So now we can use this algorithm to just calculate exactly what we're interested in. Now we can just look at the infinite temperature autocorrelation functions, or like dynamical correlation functions, which we can now use to calculate the diffusion constant. And then here we do it for energy diffusion. So we take the Ising model and just create some energy in the center of a chain. And then we just look here at the correlator between the energy, right? So we just look at the local energy at position 0 and how it's correlated with the local energy at position X. And started with like a really non-equilibrium state. So here, like these kind of funny features. And then as it goes in time, it just equilibrates and we just get a nice Gaussian from which we can then just read off the diffusion constant. And now if we just plot the mean square displacement as function of time, we see that this dotted line is what we get from our algorithm, which shows this kind of diffusive behavior. And we can now also compare it to exact diagonalization data, which, as I pointed out, is scaling exponentially with system size. But we see, at least by eyeballing, that it sort of asymptotically converges to the data that we get from our matrix product operator algorithm, for which the system sizes can be chosen as large as you like. I mean, there's the system size is no longer a limitation, so we can go to very large system sizes, and we see that it just asymptotically nicely converges to what we get. So this is now quite nice to look at, and now we can just try to be more quantitative and then really extract the diffusion constant from the long time limit of this, because here we see, for example, as we extrapolate the diffusion constant from later times, there's still a finite time behavior, so we can just extrapolate the large time limit now from this, and now we can extract the diffusion constant as function of gamma. And we know for gamma equals to 0, we are just simulating the exact stuff, but that's hard. So now we can basically extrapolate the gamma equals to 0 limit in a controlled way, and this is what's shown here. And now we just can sort of confidently extract the diffusion constant from these simulations. And that's now for the Ising model, but we can also look at another model, for example, the XX ladder. And for the XX ladder, there are some values known in the literature that we can compare to. There's this triangle here, which is from another study from CQuiC and others. And we see that indeed our our results using this method extrapolate in the gamma equals to 0 limit exactly, or like at least within a small margins to the value obtained from this other work. So and finally, and before I close, let me now show the results of some other methods. I pointed out that we are not the first to think about it, but there are other methods on the market that also promise to calculate or to simulate similar quantities. And one of them is a so-called non-equilibrium steady state method, where actually an open quantum system is considered, where it does do a boundary drive. And there's also the cluster truncated Wigner approximation, which was propagated a lot by Anatoly Polkovnikov. And now we just take these methods, all of them have some small parameters that we need for the extrapolation, and just use it to extrapolate the data. And the upshot is, for this XX ladder, basically all the methods agree within some error bar. I mean, I would personally say that the most trusted one is probably this super large scale exact diagonalization study for this model. And here Dowie, for example, is always quite close to this exact diagonalization study, and the others are pretty close in after extrapolating to the thermodynamic limit or to large cluster sizes. But then we also use now the same algorithm to an exactly solvable case like the XXZ model, which is an integrable spin chain, for which there are some analytic results by Sarang, Gopalakrishnan, and here we actually see that the other methods, like the NES method and also the cluster truncated Wigner approximation, just completely fail, and they fail for the reason that these methods can't cope with the fact that there are some rather complicated integrals of motion, while the Dowie method actually still approximately gets the diffusion constant right, even for this model. Good. I think I'm coming now already to the end. So basically what I wanted to show is that with the use of some artificial dissipation in the Heisenberg evolution, which damps complicated operators, is a tool that allows us to reduce the entanglement or the operator entanglement, and thus to simulate these systems to rather long times. And the key insight, or the key idea, is that these complicated operators will eventually not significantly contribute to our observables. And yeah, let me then close by maybe thanking my collaborators, maybe Tibor and Kurt, for this nice collaboration, and thank you for your attention.
Fantastic talk. Thank you, Frank. Are there any questions?
Yeah, I have a question if I could.
Sure.
They were really quite interesting, Frank, and really very much along the lines of things we were chatting about. So I'm very excited to see this. So I guess I have two different questions. One thing I didn't understand, when you do this effective truncation of the operator entanglement, you said that we could, in principle, then map this back into the sort of the Schrodinger picture and think about a matrix product state, if I understood correctly.
I'm not sure. Yeah, go ahead.
Okay, so yeah, maybe I was confused about that, because, you know, if at the end of the day it's kind of equivalent, if maybe I misunderstood.
No. Let me just.
Yeah.
Let me clarify it. I right. So maybe it's. Opla. No, wait. Let me go back to this picture. But what I meant to say is the following. It's basically shown here. So if I'm just using now the graphical notation, now this would be a matrix product operator, because it's now something that's acting on my vector space. By saying that I can represent it in terms of an MPS is by saying that, well, let me now bend over the picture. So this is not at all
I
the
see.
Schrödinger picture.
I
It's
see.
just that I'm saying that, well, I'm using the matrix product.
You're vectorizing. You're vectorizing the operator, and then that's it.
That's exactly correct. So
Yeah,
I'm
okay.
vectorizing the operator, and then I'm using the matrix product state formalism, but it's
Right.
not at all the Schrödinger picture.
All right. So I have a second question, which I'll take my privilege to. Is so this very nice model, of course, is also an exact dissipation model. If you had a depolarizing channel, this is exactly what would happen. And actually, there's this recent work looking at the polynomial algorithms for quantum sampling of random circuits that you may have seen. It's got a little hype. So my question really is, so, you know, the question is, how robust is the diffusion constant that we would want to extract for the closed quantum system, for the Hamiltonian system, compared to the diffusion coefficient that you would see in the presence of actual, say, depolarizing channel, which would be modeled exactly by this model of damping out the high Hamming weight Pauli operators. And does that telling us something about the complexity of the problem, if it's in some sense somewhat robust to decoherence, and so that we can extrapolate back to the closed quantum system, that in some sense it was easy and we didn't need a quantum simulator to do it? But the problems that are where this dissipation will really very much change the answer compared to the closed quantum system are ones that a NISQ machine or a dissipative system would get the answer wrong. I mean, maybe that's related to the backflow picture that you have of which of these important paths you need to keep. I don't know if the question was clear.
No, I think it does. I mean, first off, I can't give you a very precise answer on this question. I mean, I can say a few things. Is that in the second paper that I had on the list, we just tried to estimate a little bit how the scaling is, and basically what we can argue is that for small gamma, that there should be some regime in which we just get basically like a linear contribution here. So that's why we have a reason to hope that you just at some point will reach a regime where you can do this linear extrapolation. So basically, if you just think of this as being like a physical system where you have these depolarizing like these dephasing channels, then you would like to get into this linear regime. But I can't really tell from first principle how to predict what this regime would necessarily be.
Yeah, it's very interesting. Great, thanks. I'll let others chime in with their questions.
May I ask more questions?
Sure.
I think let's let Tamim go first because he's got his hand raised and we want to reward his behavior.
Sure.
Thank you, Zula. And thank you, Frank, for the great talk. So my question is kind of maybe an offshoot of Ivan's. So if I wanted to think of this as a realistic open system model, like, do you have a sense of what the steady state of the system is? Like, if I was to look at the sort of the thermal state of that describes local observables, let's say, what is the temperature of that thermal state?
Well, at the moment, the assumption is that we just do this at infinite temperature. So this is actually one thing that we are quite interested in, but we haven't really done a lot of work in this direction, is to see that, well, now what we can do, for example, here, let me just go to the original expression here. So what we could do in principle is that we just now insert here so we could insert here an e to the minus beta h or something like this to go to finite temperature. And the question is how well that would work. And I think that the method, the way it's done right now, is sort of tailored to high temperatures, but I don't know when it would break down. Does it make sense? Because if you just go you can, for example, construct cases where you would see that, I don't know, if you, for example, take some sort of Ising type model where you just have a ferromagnet, the excitations would be domain walls, and these domain walls would just consist of extended regimes of sigma z strings, and those would be super relevant, and those would be killed off by these dissipators. So then clearly it would fail working at very low temperatures for those cases. But I don't have not much very general to say about it.
Okay, thank you.
All right, and before Anupam asks, yes, you've got your hand raised. I'm going to demonstrate bad behavior and ask a follow-up question to that, because I've been puzzling over this too, similar to Ivan and Tamim's question. So why, I think I just sort of missed it. Why do we think this artificially making the system open will adequately model these correlation functions? Was that the wandering off? Or yeah.
Yeah, exactly. So the intuition is exactly this one. So I'm in the operator space, and so let's even go back one more. So now I'm just expanding my operator in terms of these polystrings. Now, if I'm at infinite temperature, this here just amounts simply to the trace. And I know that these polystrings are orthogonal, right? So basically, if I'm, as I also shown before, like, so if I start from something like this, and in the end I measure this, then only projections onto 1,1 as the 1,1 will survive. And the intuition is that if now some operator just wanders off and it becomes here some operator which is x, z, 1, x, y, and so on, that of course there's a certain chance that it will just shrink back to a very small operator. But the assumption, and this is also what we can partly show analytically in the second paper, is that the probability of a large object to go back is exponentially suppressed.
I see. And it's just matching this exponential suppression to a dissipation, or to this artificial dissipation.
Yeah, exactly. So this we show here. If you just look at these autocorrelation functions, basically, or the contribution to the, so in order to measure the dissipation, you are just calculating the autocorrelation functions at long times, right? So basically now, and what we can show here is that the corrections on the error on these correlation functions is actually exponentially suppressed. And that's the reason why we believe that the effect it has on the, right? So the diffusion constant is obtained by just fitting this here, right? So this is now the correlation function. We show that the error on this is exponentially small in L star, and then the assumption is that the diffusion constant can be meaningfully extracted.
Yeah, thank you. I follow that very well. Anupam, your question.
Thank you. And thanks for the great talk. I really enjoyed this. My question, you sort of answered it, but in bits and pieces. But if you could just put it all together, that would be great. So it's like, let's say I'm given a Hamiltonian. Of course, with that come conserved quantities, and I want to calculate a diffusion coefficient for it. How do I go about choosing L star and gamma in order to do that?
Right. Okay. So the answer is, based on what we learned so far, that first of all, you have to choose L star larger or equal than the support of the quantities that you want to look at, right? So let's say that you have a system which, as in this case, you have energy conservation. You have to have L star at least equal to 2 or larger. Because if L star is 1, it would just, the dissipator would basically kill energy conservation. So this is the thing, and that's why here for, if you just have this XX letter where we're only interested in total SC conservation, we can even just do L star equals to 1, right? So if we in this case were to use L star equals to 2, the energy correlation function would go down exponentially, and we wouldn't get anything meaningfully out of it. So this is the one strong requirement on it. But then for these cases, that seems to be the only thing. So you just find that independent of L star, all of these values converge to the same value, right? So here the only requirement is to just choose large enough such that the conserved quantity is not destroyed. Now, there are other cases where we have to be more careful, and I sort of glanced over it very quickly. But this is still important, because now take the XXZ chain. The XXZ chain has, besides the local conservation laws that you might be interested in, like in this case, total SZ, it is an integrable model. So it has these integrals of motions, which can be much more complicated. And here things are now getting a bit dangerous, to be honest, because now if we look at this one here, like the lower plot, we plot the values for different L stars, and we see here that if L star is 1 or 2, we would actually extrapolate the wrong value, and only if L star is 4, we actually just get the right value, which means that there are now these integrals of motion in this integrable model, which are destroyed if we just use L star too small. And this is, to be honest, a bit of a dangerous thing, because it tells us that in order to be sure that we are just getting the right value, we do have to explore a certain range of these L stars. And probably what we would like to do, but that's actually quite hard, is we would like to just choose L star very large. We would just like to choose L star from, I don't know, 1 to 15. And then we want to see that it maybe doesn't change between 4 and 15 to be just confident that this is actually the correct value. This is actually a weakness that we have to be, like for integrable models, have to make sure that our L star is sufficiently large to obey the relevant, or to just keep the relevant integrals of motion. And either you just, if you have a completely unknown model, what you would have to do is to just push the limits to very large L star, or you need to put in some additional input that you have about the model. I'm not sure if this is a satisfactory answer to your question.
No, it's satisfactory. Thank you. I have a follow-up question. May I, or maybe Chaitanya goes first?
Yeah, thank you. Excellent talk. I just had a very minor question regarding this plot and the comment that you made. Is there a reason why L equal to 4 works here?
Good question, and I can't give you the answer. So I mean, my suspicion is that this is due to the fact that, like, if you just look at the XXZ model, which is an integrable model, so it's like a beta ansatz integrable model, you can just write down the conservation laws. And my suspicion is that L star equals to 4 corresponds to the size of the integrals of motions which are relevant here. But I don't know the exact solution good enough to tell for sure.
Okay, yeah, thank you very much.
Actually, okay, go ahead, June.
Thank you. Sorry. Thank you for the great talk. Another question with this plot is that So the CTWA, it seems like it's a little hard to see, but I guess it's also converging to something like quite smaller than the correct value, which is 1.0. So like, does that actually, like, are they actually close to the values that the L star equals to 1 or 2 are converging to, and like also the Ness method is converging to? Like,
no, the L star equals to 1 or 2 is still not in this range. Like if you could have all these plots are on the same scale. So you see that the value is actually significantly below what the L star equals to 1 or 2 gives.
Oh, okay.
So the artifacts we get from the cluster truncated Wigner approximation are actually quite different.
I see. Can I also ask a very naive question? Why does the Heisenberg picture become way better in terms of handling like unnecessary highly complex ones compared to the Schrödinger picture? Is it just because you're not dealing with a specific state?
Right. I think that this is so the reason why, I mean, not sure this is the best answer to your question, but I mean, for this Heisenberg picture, I thought of exactly this idea. I thought that, well, in this Heisenberg picture, I just know how to write down a dissipator that doesn't affect my conservation laws, because it would then commute with the Hamiltonian. And I thought of this backflow correction. I thought that, well, if things in this picture become very complicated, it's very unlikely to go back. And I wouldn't know how to do this in the Schrödinger picture. But this is not mean, it doesn't say that it's impossible. It's just that I thought this direction, and I had a hunch it might work, and then Tibor basically showed that it actually does work. But I'm not excluding the possibility that it's also possible to do it directly in the Schrödinger picture, but I wouldn't know how to do it.
I see. Thank you so much. So I guess the basic thought process was that, well, dissipation is like one of the very important macroscopic features, or the hydrodynamic level feature, and that has like is basically caused from the conservation laws. So like you should have some kind of a method that at least totally respects that conservation law and still gets rid of the unnecessary part, and that kind of naturally led to the Heisenberg picture.
Yeah, and also, I mean, add to this, I mean, before we worked on this also together with Tibor and Kurt, we looked at basically at operator spreading, and from this work we were quite used to think in terms of operator evolution, right? So there too we were doing basically everything in operator space, and that told us a lot about the kind of physics of operator evolution. So that basically guided us to this.
I see. Thank you so much.
I think in the interest of time, let's thank Frank again and conclude our seminar.
Yeah, thanks again for the invitation, and also for these